Good morning. Well, good morning, everybody. I'll start in a few minutes. All right, folks, it's 9:30. We'll get started. So Module 6 is about chemical reactions. I'm actually going to skip over this part on the balancing because we're going to be doing balancing while we go anyway. So I'm going to leave you to handle that on your own. There are videos here, and there's also a good exercise here that will be good to test your theory on balancing. I will mention one thing. Let's say we had something like V2O5 plus Ca, because this is going to matter for what we're doing. Okay. So if we have something like V2O5 plus Ca gives CaO plus V. Now to balance this, the only way I can ever balance anything is to put numbers out in front of compounds. One thing I couldn't do, for example, is just put a 5 down here on the CaO, make it CaO5. I can't do that. It's illegal. What I can do is change the numbers of moles of things. And I do that by putting numbers out in front. So I can put a 2 in front of the V here. I can put a 5 in front of the CaO like that. And then I can put a 5 in front of Ca. Now, the way that I usually test balancing is by using this sum of coefficients. Now, we usually don't put a 1 out the front if there is a 1 out the front, but we know it's there. And sum of coefficients for this one will be 1 plus 5 plus 5 plus 2, which is 13. So that would be the answer for that one, would be 13. So you just go ahead and you match these up like that, and it will give you the right response. All right, does anybody have any questions? Yes, that is a good exercise to practice your balancing technique. Now we're going to move on here to predicting the reactions of acids and bases. Oops, wrong screen. Okay. Do anybody have any questions about that sum of coefficients? Okay. Now, there are going to be problems where you're dealing with acids and base reactions, and what happens with acids and bases is they're generally reactions of this type, where you've got HX plus YOH, and you end up getting YX plus H2O. Now, you might be wondering why I said YX, and that's because we always put the cation first. So in the case of YOH, that's the cation, and X would be the anion, so that's why I've got YX. Now, the combination of Y and X, that's what we're going to focus on here. So generally speaking, we're dealing with things that have H at the start of them as H+. Sometimes the H is in the middle of the compound like this, NaHSO4, CaH, CO32. And bases have OH in them, like NaOH and CaOH2. Now, on any test I give you, I tell you it's an acid-base reaction, so you always know exactly how to treat it, and you are on the lookout then for the H+ and the OH-, so you can join them together to form the water. So the water here is from the combination of the H+ and the OH-. So both of those together will form that water. And there's your H, there's your OH there. So those are the things that are combining to form the water. All right, any questions so far? All right, let's look at a couple of examples here. We'll do NaOH plus H2SO4. And what we're interested in is what the reaction looks like. Now on the test, I'm more interested in what these two compound, well, what the compound is that goes with the water. So it's always water and what we're calling a salt. And the salt here is going to be a combination of an anion and cation. So how do we handle something like this? Well, what we do is we try and draw a picture of it and put the charges on things. So we'll have NaOH, which is going to be Na plus and OH minus. And if we had H2SO4, that'd be two H's and an SO4. The SO4 is -2, and the pluses are going to be on those two hydrogens. Now, as far as the charges go, remember that you'll have a polyatomic ion sheet, so you'll know what the charges are on OH and SO4, so you won't have to memorize those. And the other thing is, of course, what we were talking about the other day in Module 5, is that any compounds we're dealing with will always have positive and negative charges that match. All right, so I'll stop there for a second. Does anybody have any questions? Now, what you should do is go ahead and circle just one of each of everything. Now, notice this is important that I only circled one of the H pluses here, not both of them. So I know what's going to happen is the H plus and the OH minus will join together. That'll give me my water. But what I'm interested in here is what else is combining together. And it'll be the Na plus and the SO4 2 minus. Now, of course, you can see that that's not going to balance out because the charge on Na is 1 plus, the charge on SO4 is 2 minus. So what I have to do is take that and figure out what it would form if it was balanced, then to be Na2SO4. So this is how the reaction would look so far. And this is usually where I lose students. This is where I lose them. Because what students are saying to me, or right now, they're saying, well, look, how can you just pull another sodium out of thin air and put it in there and it's not even balanced? Right? I mean, I know that's what some of you are saying. You're sitting there saying, well, hang on, how's he doing that? Well, the thing is that the priority first is balancing whatever salt we get with the water, and then we can balance the reaction. Now, to balance this, then, I would put a 2 in front of here, in front of the NaOH, and then a 2 in front of the water, and that would balance the reaction. So we'd have the same numbers of hydrogens, oxygens, sodiums, and sulfurs on both sides of the reaction now, and that would be balanced. So the focus first is on figuring out what that is, the salt, the Na2SO4.
You can find your phone.
All right, does anybody have any questions? No, somebody needs to mute. Having a conversation here. I'm not sure who it is. Might be, well, I don't know. Kaylee, possibly. All right. Anybody have any questions?
So with a salt is basically always going to be a cation and an anion, and that's what they classify always as a salt, basically.
That's right. It's
Okay.
whatever you get when you add everything else that's left over together, aside from the water.
Okay.
All right. I'm going to do another example here. Let's see, something a little bit more difficult, say something like this. All right, so this is a really good one to do. MgOH2 plus H3PO4. So I draw pictures of these, and it's going to be Mg. Well, I won't put the charges on yet. We've got Mg and 2 OHs. The OHs are each -1. That makes the Mg +2. And then we've got the H3PO4. Which looks like this with 3 H's and the PO4. So the OH minus and the H plus are going to join together to give water. And then the Mg2 plus and the PO4 3 minus join together to give the salt. Now this is the part that I think really annoys students because I only take one of each of these. And I know the temptation is to say, well, why don't you add all of these together to give something like H5O2? Well, because if we don't get that, we get water. That's the product. Where our focus is figuring out what the compounds are first, and then we balance the reaction later. So we only take one of each cation and anion here and join them together initially, and the H plus and the OH minus will form water, and then the Mg2 plus and the PO4 3 minus, if I needed to form that compound would be Mg3PO42. And it's like what we're doing the other day. We have to figure out how many of each we need to make that compound even out, to make it balance. Does anybody have any questions?
How can you tell the difference between, like, how do you classify a base?
A base always has OH.
A base always has OH on it. Okay.
Yeah. And the acid will always produce H plus somehow.
So yeah, so acid will always have like hydrogen in it, and a
Yes.
base like
Yeah.
hydrogen in the front, and then it'll have
Well, not necessarily in the front. It could be in the middle of the compound, something like this here, which I'll do in a second.
okay.
Right. But it's always forming H plus. Acids form H plus. Bases always form OH minus. When you take an H plus and OH minus, you put them together, you get water.
Okay.
Now, if I wanted to balance that, and this is where I would take all this stuff into account. I've got 3 Mgs here, so I put a 3 in front of the MgOH2. I've got 2 PO4s here, so I put a 2 in front of the H3PO4. And that means if I count up the oxygens, I've actually got 6 oxygens here and 6 hydrogens, and then another 6 hydrogens here. So a 6 in front of the H2O will balance that reaction. But the main thing I want you to be focusing on, at least initially, is how we get that compound that goes with the water. Does anybody have any questions? Okay.
So I usually when I balance stuff like that, I just put OH by itself and then H in front of it. Will you like gig us for that with points and stuff or no?
No. Well,
Okay.
it's not. Besides, these are multiple choice, and I'll
Oh,
show
okay.
you know, when you're doing it. That won't be an issue for you.
Too easy. Just want to make sure.
Okay. Well, it's not as easy as you think, multiple choice. It's cruel multiple choice. I think my multiple choice is crueler than any I've seen anywhere. It's so hard to guess. You know, you've got to actually know what you're doing. It's really tough. All right, so let's look at what this looks like as pictures here. Now we need a HCO3 2. Okay. Okay. Now the H's here are actually H pluses. And we've got Ca and then OH and OH. And the Ca here will be 2 plus. And I'm going to leave the CO3s without a charge for a bit here because it's not really relevant. So the H plus and the OH minus will join together to give water. And what's left over is the Ca2 plus, and now I'll put the charge on the CO3, and CO3 2 minus. That's the charge there. Yeah, these are a little bit trickier because you have to be able to know that that H there is an H plus. And the reason you will know that is because I tell you it's an acid-base reaction, which is why you would pull out that H plus from the beginning there and add it to the OH minus. Now, so to balance that, I put a 2 in front of the CaCO3 and a 2 in front of the H2O, and that would be balanced. So that's an example of one where the H plus is sort of in the middle of the compound.
Where did you get 4 H's?
4 H's, let's see, 2.
Because in the first one, it's
No,
like
I'm looking. Hang on. So we've got two H's here and then two H's here. So what's your question?
Oh, so like in the beginning, you drew out like four H's when like it's CaHCO3 when
Oh,
really
no,
there's
no.
like.
I was actually, what I was doing was I was taking these and sort of making them 2H pluses. If I wanted
Okay.
to, I could put pluses here as well. You know, it doesn't really matter. I was just trying to say they were H pluses.
Okay. Okay. Makes sense.
Okay. Any other questions about that one? Okay. So on the test, your main focus, again, will be finding this compound here. Whatever this compound is with the water. Not so much the balancing part. All right, so combustion of hydrocarbons. So hydrocarbons always have the formula CXHY, which makes sense because they're hydrogen and carbon, hence the name hydrocarbon. And as you can see here, the products are always carbon dioxide and water. So there's two flavors of this question that we can talk about. I'm going to do examples of both of them because I think that's the easiest way of showing you this. I'll do this one, C2H4 plus O2 gives CO2 plus H2O. And the other one I'll do is C6H6 plus O2 gives CO2 plus H2O. So focusing on example A, here's how this works. We've got C2H4 plus O2 gives CO2 plus H2O. Again, you don't have to memorize that. This is given to you on the test. So we put a 2 in front of the CO2 to balance the C. We put a 2 in front of the H2O to balance the H. Remember, there's 2 H2O. That's a total of 4 H's to balance the H. I'll stop there for a second. Does anybody have any questions? The hard part is balancing the oxygen because on this side we've got 4. 2 times 2 is 4 plus 2 is 6. So that means I put a 3 in front of here and that would be balanced. So that one's not too bad. Now B, this one's a little bit more difficult. Now I'm going to do the same thing as I did previously. I'll put a 6 in front of the CO2. I'll put a 3 in front of the H2O. And that balances out the carbons and hydrogens. Now the oxygens are a bit more of a challenge. We've got 6 times 2 is 12 and 3 times 1 is 15. So 6 times 2 plus 3 is 15. And you'll notice here I've got O2. So that's not going to work out so well. So what I do is I do 15 halves or 15 over 2 O2. And that will balance my oxygens there. Now since we don't like having fractions in our balanced equations, what we do is we multiply everything by 2. And that will end up balancing everything out. So that would be the final balanced equation. If you count it up, you've got 2 times 6 is 12 C's, 12 C's. You've got 2 times 6 is 12 H's, and then 6 times 2 is 12 H's. We've got 30 oxygens, 15 times 2, and then we've got 12 times 2 is 24, plus 6 is 30. So we've got 30 oxygens on each side once we handle that. Does anybody have any questions about this, about doing any of that?
So you want us to double it and you want us to make it all even. You don't
Yeah,
want
that's
any
right.
fractions. Okay.
That's right. No fractions. No fractions. Now, a good question would be, well, how do you know when you need to multiply by 2 and how do you know you won't? Well, it's actually an easy way of looking at it. What you do is you look at the number of hydrogens. If a number of hydrogens, when you divide it by 2, comes out to be an even number, then you won't have to multiply by 2. But if you take 6 here and divide it by 2, you'll get 3, which is odd. So if you take that number and you divide it by 2, and it's an odd number, then you know at some point you're going to have to multiply by 2 in order to make that even out. So it's a good little rule of thumb to know. Let me show you an example down here. Okay. So what I want you to do is, I want you to go through these with me and tell me if we're going to have to multiply these by 2 or not when we balance these. Okay, so C7H8, we'll have to multiply that by 2 at the end?
No.
No, because 8 divided by 2 is 4. What about C5H12? Well, that has to be multiplied by 2.
No.
No, because 12 divided by 2 is 6. That's an even number. What about C6H8?
No.
No, that's 8 divided by 2 is 4, so that's an even number. What about C7H10?
Yes.
Yeah, because 10 divided by 2 is 5, that's an odd number. And we already did this one. What about C6H10? Yeah, it's the same as that one. So yes, the answer is yes, we would have to multiply 2 by 2. What about C6H14?
Yes.
Yeah, 14 divided by 2 is 7. All right, so that's how you can easily tell if you're going to have to multiply by 2 at some point during the process. All right, any questions about hydrocarbon balancing?
So it will always produce CO2 and
Yes.
H2O, and
Yes.
there's no instance where it produces anything else.
No. And the other thing I'll tell you is that on the test, I tell you that, so you don't have to memorize it.
Okay.
Okay. Double displacement reactions. Now, these are very similar to acid-base reactions, except we're not getting water as a product. Instead of getting one salt, we're actually getting 2 salts as products. This can be a bit challenging. So let's look at a question. And I'm just going to go through one question of this type, but on the test, I split this up into different parts. And then at some point, obviously, I'll go through the test and I'll show you exactly what kinds of questions you're going to be looking at here. All right, so let's look at this. We've got PbNO32 and Na3PO4. So we've got 2 compounds here. They both consist of anions and cations. And in a double displacement, you can think of it like 2 couples dancing, male-female couples dancing, and then the males and females switch partners. It's kind of like that. So what I'm saying here is you've got lead, which is a cation, nitrate, which is an anion, sodium's a cation, and phosphate is an anion. So what happens here is the Pb combines with the PO4 and the Na combines with the NO3. So that's the basics of what's going to happen here. So what we should do is draw out pictures of these along with their charges so we can figure out exactly what's going on. So the NO3 has a -1 charge, and again, we get that off the polyatomic ion sheet, and that's something that you'll have in front of you, so you don't have to memorize that. That means the lead must be 2+. The sodiums, well, the PO4 is 3-. That makes the sodiums all 1+ each. I'll stop here for a second. Does anybody have any questions? So we know what's going to happen is that the Pb2+ and the PO4 3- will join together, and the Na+ and the NO3- will join together. Now you'll notice again, I'm just taking one of each here, not all of these, and trying to balance them out. So the Pb2+ and the PO4 3- will join together, and the Na+ and the NO3- will join together. Sorry about that. Went too close to the edge there. I'm always going too close to the edge, I think. So if you've got Pb2+ and PO4 3- and you want to figure out what compound that would make, it's whatever it takes to make that even out. So to be Pb3, PO4 2 would be the compound we'd get there. And then the Na+, NO3-, that just needs one of each. So to be NaNO3. So the final reaction we have before balancing of the reaction looks like this. PbNO3 plus Na3PO4 gives Pb3PO4, whoops, 2 plus NaNO3. Okay. Does anybody have any questions so far?
I have a question.
Yeah, yes, Haley.
Where did you get the 3 for the PB and the 2?
Okay, so you can see that the charge on PB is 2 plus and the PO4 is 3 minus, right?
Yes.
So the question you're asking yourself is, how many of each do I need to make those charges even out? So if you've got plus 2 and minus 3, it's kind of like a common charge of 6 is what's needed. So you'll need 6 positives and 6 negatives. And I know that because it's 2 times 3, right?
Yeah.
Okay, so we need three leads and then 2 phosphates to make that happen.
Okay, I understand. Thank you.
Okay, so the main thing here, and I see this happen all the time, is that people will try and join all of these together to get some massive compound that involves a bunch of NAs and a bunch of NO3s. But what we're interested in here is just what the combination of one of each of those would represent, and then figure out how many are needed in order to make that charge even out. That's what we did here for the lead and the phosphate as well. Does anybody have any questions so far?
Are you going to balance it?
Yes, I am.
Oh, okay, I
Yeah.
just didn't. Okay.
Yeah, I haven't balanced it yet.
Okay.
So I've got 3 leads over here, so I need to put a 3 in front of the PB over here. I've got Na3PO4, so I need a 3 in front of the NaNO3. And then if I'm going to leave the 3 there for now. But over here, yeah, that balances my sodiums. Now I've got phosphates here. I've got 2 of those, so I need to put a 2 in front of here, in front of the Na3PO4. But now that means my NaNO3 isn't balanced. I need to change that to a 6. So that would be balanced now. We'd have 3 in front of the PbNO3, 2 in front of the Na3PO4, then PB3PO4 2, and then 6 NaNO3s. Does anybody have any questions?
What is the difference between a ionic equation and a net ionic equation?
I haven't gotten to that yet. I'm getting to it, David.
Okay.
So we've got our full equation here, but we haven't split it into ions or anything yet. That's what David was asking about, but we will do that in a second. But the other thing we need to look at is generally during these double displacements, we get something that forms a precipitate, a solid that comes out of solution. And we need to be able to figure out which of those is going to be solid and which is not going to be solid. And to do that, we use this chart here, which is a solubility chart. And you'll notice, looking at the key, aqueous is AQ and I is insoluble or partially soluble, which means it's going to be a solid. Now, aqueous means it splits up into ions, and solid means it forms a solid. Now, typically, if you've got something aqueous, then it doesn't look like anything is in the container. It just looks completely clear. Whereas a solid, of course, is going to be solid. But looking at that, if I combine lead and phosphate, where is that? Here we go. Lead and phosphate, you see it comes up to be an I. So that means that this is going to be insoluble, which means that gets to be a solid. And sodium and nitrate is going to be aqueous. So that's how I know that that's going to be solid and that's going to be aqueous. You don't have to memorize this. If it's required, it'll be given to you. So this is not memory work. But it is an important step because we do need to know what's solid and what's aqueous. Does anybody have any questions about figuring that out?
Is it possible to get two insoluble compounds when you're doing a double displacement reaction?
I suppose it's possible, but generally speaking, we usually end up with just one or none even. It's possible to end up with none.
So if you're doing a double displacement reaction, if you get one that's aqueous or insoluble, you can pretty much guess that the other one is the opposite.
Yes, I'd say
Okay.
that's true. Yeah, 99% of the time that's true, but 100% of the time on your tests, okay?
Quick question.
Yeah,
Is there
yeah.
any way to do without the chart just by looking at the compound itself and saying like, oh, that's ionic, so it's probably going to be Ag because it's going to be soluble in water or whatever, or
No, not really.
so you just have to go off the chart
You have to really
basically.
go. There's too many exceptions. I mean, there are
Okay.
some standard rules, like all nitrates, for example, are soluble. You notice all nitrates are AQ, for example. But you know, all the other ones, there's just too many exceptions, and I just wouldn't want to deal with it.
Gotcha. And now, does this chart only include like non-metals reacting with?
No,
These
well,
are the
no,
most common, right?
these are the most common ones. There are mixtures here of polyatomic ions and single element ions here as well. You've got sulfide, oxide, chloride, and bromides as well as all of these different polyatomic ions.
So if I wanted like a larger database, I'd have to probably look
Oh,
for
you'd
one.
have to
There's
look it
probably
up. Yeah, have
okay.
to use Mr. Google.
I gotcha. I just didn't know if like one exists and that's how you guys did it, or like if there was a certain
Nah,
classification.
not real. Well, I mean, there's rules, and you know, you could know the rules, I suppose, but you know, they're
That's later
annoying.
down the line.
Well, they're just annoying. I mean, why learn to memorize a bunch of rules when you can just look it up?
That's fair.
All right. So looking at the other things, we need to write a full ionic equation and a net ionic equation. So we'll do the full ionic equation first. And with the full ionic equation, what happens is that the aqueous ions will split into ions. Now, solid does not split. And that's key. That's key. So an aqueous compound, as I told you, you don't see anything in the solution. It looks completely clear. Whereas with a solid, you see a solid. And the reason it's solid is because it's not splitting into ions. That's the whole point. That's why we get what we get out of these. So how do we come up with the ions that go along with that? Okay, I'm going to see if I can scroll down a bit here. And let me change the canvas here a little bit. Okay. All right. So PbNO32, let's look at what one of those looks like first. So that'd be Pb and two NO3s. The NO3 is -1 and the Pb is 2+, but there's actually 3 of everything here. So we've got 2 of the Na3PO4s. And again, you'll notice I'm splitting these up into ions. The same ions as I used at the very beginning of the problem. If you look at that. Now the Pb3PO42, we agreed that was a solid. So I'm going to leave that as it is. It doesn't split into ions. And then we've got the NaNO3s, and there's 6 of those. And that's going to be Na plus and NO3 minus. Sorry about that, trying to squeeze it in. Okay, I'll stop there for a second. Is anybody confused by anything I'm doing right now? And why I'm doing it?
Yeah, I'm confused. What are you doing exactly?
Well, I'm splitting anything that's aqueous into its component ions.
So you're splitting. Isn't both PbNO3 and Na3PO4 aqueous? Are you just splitting both of those, or what
I
are you
am.
doing?
I am. That's exactly what I'm doing. But
Okay.
you'll notice, David, I didn't split up the Pb3PO4 too because it's a solid.
Oh, so I guess that's what remains.
Yeah, that's right. So
All right, that
everything
makes
else
sense.
just looks like it's dissolved in solution. You can't even see it.
Okay, just clear.
Yeah. Just clear. No solid. In the aqueous ones, yes. So initially, when you've got these two, PbNO3 and the Na3PO4, they're separate. They just look like clear colorless liquids. And then when you add them together, you get this solid. And that's what's going on there. There's also going to be the sodium nitrate. That's going to be dissolved as well. Anybody else have any questions? So now
what you're saying
yeah, go on.
is so when you dissolve, so you're only going to do that when it dissolves in water. So like say you evaporate all the water and stuff like that, they would go back into the
Oh,
aqueous
yeah.
liquid.
Yeah, that's right. They
Okay,
would,
so that water would, the water would be ionized basically, right?
No, well, no, the water is doing the ionizing.
Mm-hmm.
Yeah, so it's in the water solution. The water's doing the ionizing. It's like if you take salt, sodium chloride, stick it in water, it dissolves, right?
Great.
Same deal.
Okay.
I mean,
So like, well, I guess the question I'm trying to ask is like, so like basically what would happen is like if you evaporated, these would become three separate liquids and they would combine together to create these compounds.
no,
If they're outside of
no.
water.
If you did the water, if you got rid of the water, then you'd have
Mhm.
just a whole bunch of these a mixture of solid salts. That's all you'd have left at the end. That's because the water would be gone, and you just
Mhm.
have these white solid salts all mixed together.
Okay, so these are all solids then if they're out of water?
Yes.
Okay, that
Yeah.
makes sense.
Yeah, they have jars. You buy them in jars, and then in order to make aqueous solutions, they have to be dissolved in water.
Okay, so aqueous has to be in water. That's what
Yes.
makes them aqueous. Okay, gotcha.
Yeah, like aqua water, right?
Gotcha. Thank you.
Now looking over here, what I do is I have to count up how many ions I have of each. So that would be 3 Pb2 pluses are going to be in there. That'll be 6 nitrates plus 6 sodiums, Na pluses, plus 2 phosphates. That gives the Pb3PO42 solid, and then plus 6 Na pluses, plus 6 NO3 minuses. All right, is anybody concerned about where I'm getting any of those numbers from? You have the numbers out in front there, the 3 to 6s and the 6 and 2. Any concerns? You're all okay with that, huh? All right, that there is a full ionic equation. A common question I get from people is, oh, do you have to put the charges on? The answer is yes, because ions are charged particles, and in order to have a full ionic equation, you have to show the particles. You have to show the charges. So that's the full ionic equation there. Does anybody have any questions? Okay, the next one there is the net ionic equation. That's actually not too bad. The net ionic equation, what it does is it takes into account and gets rid of anything that's the same on both sides of the reaction, what we call spectator ions, things that don't change, things that are going to be aqueous on both sides and really don't need to be there. So what I can do is I can chop out the sodiums and the nitrates, and all I'd be left with is 3Pb2 plus 2PO43 minus gives Pb3 PO42 solid, and that would be the net ionic equation. But put more simply, the net ionic equation is always whatever forms the solid, whatever ions are forming the solid. So it's not really that hard to come up with one. You don't have to do all of this stuff here. You don't actually have to do a full ionic equation to get a net ionic equation. All right, does anybody have any questions about that?
Could you explain the net ionic equation one more time?
It's whatever combining together to form the solid.
So it's just that then.
Yep. And
Okay.
you'll notice that, you know, anything else that's the same on both sides ends up canceling out anyway. So it's just like a regular equation, you know, a math equation. When you've got like terms, you can always cancel them out, right?
Okay.
Two seconds. Jonathan? Yeah, I'll contact you later. Right? Yeah, fair enough. Sorry about that. All right, any questions? Okay.
So the full ionic equation is just each individual, I guess, element.
Or no,
or
anion and
not-
cation that makes up the solid.
Yeah, right. First, each individual cation and anion that combines together to form both the solid and the aqueous, while the net ionic is only the solid.
That's right. Yes, that's right. Yes.
Okay.
So the full is everything. The net is just whatever's forming the solid. That's right.
Kind of the full ionic equation is just a FOIL method of the whole equation, right? You're just foiling it out.
Oh, you can look at it that way, yeah. Whatever floats your boat. Okay. Well, let's look at decomposition reactions. And there's actually a couple we're going to look at here. Now, a decomposition reaction is something where you've got two things that are joined together in a compound, and then when you heat them, they turn into two different things. They turn into things that were part of the original compound. The ones we're going to focus on here are going to be chlorates and perchlorates. And then I'm going to show you some other ones that I throw in for General Chemistry 1 that weren't in Intro to Chemistry. So the main ones we're going to focus on will be those chlorates and perchlorates first, and then we'll look at some carbonates and some hydrates and hydroxides as well. Okay.
Can they go the other way if there's a loss in energy?
Yeah. Oh, yeah. I mean, I suppose, you know, these. What happens is usually when these perchlorates, well, they're heated to form these. I suppose, yeah, you could combine them together, but yeah, usually it doesn't go that way.
So usually they only separate when energy's added.
Yeah, and the reason for that is because these chlorides tend to be very stable. They tend not to want to recombine with the oxygen.
Gotcha.
All right, so the general formula of these, and I'm going to use this as X's here, and the people don't usually like this, but I'm going to do it anyway. Whoops, what the heck's going on here? Oh, that's not what I want. I think this is stretched out here for some reason. This is not pleasant. Okay. Sorry about this. It's not being very cooperative with me here. Okay. All right, let's try that. That should be all right. Okay. That's better. A little bit better. Not what I had before, but it'll do. So X ClO3 will give XCl plus O2, and XClO4 will give the same thing. So what we get is always a combination of some sort of chloride and O2. And we know what the charge on the chloride is. ClO3 is always 1 minus, and ClO4 is always 1 minus as well. So let me show you some examples of these, and you'll see they're not really as bad as they initially seem. Let's say we've got XClO3 4. We'll go with 4 here. And I want to figure out what the products are of that. Well, I know that if I drew a picture of this, it would be X4 plus and then ClO3 minus 4 times. So the compound would be made of X4 plus and Cl minus. Therefore, it would be XCl4 would be the metal I would get from that. It doesn't matter what X is. I mean, it could be anything. But what I'm saying is we know what the charge on X is because we know what the charge on chlorate is. Same with perchlorate. It's always going to be -1. So the charge will always match however many you have of the chlorates or perchlorates.
And then there would be
Now,
how many oxygens at the end?
Oh, I'm just about to do that.
Oh, okay.
Just enlarging my screen here so I can manage that. Okay. So to do the final balancing here, once we figured out out the formula of the solid there, so it's XClO3 4 gives XCl4 plus O2. So we look at the number of oxygens here. We've got 3 times 4 is 12, so we need a 6 in front of the O2 here. All right, any questions about that?
What is this called specifically?
Decomposition.
Oh, okay. Decomposition.
Yeah.
Predicting about. Okay.
Okay, I'm going to do another example here. All right, what if we had this one is probably one of the more difficult ones. XClO3 5 plus O2. Can anybody tell me what the formula of the chloride is going to be? You should be able to tell me pretty much off the top of your head here. If we know that chlorate is a -1 charge and chlorine, Cl minus, chloride is Cl minus, what would be the formula of the chloride? We know we're getting plus O2 as well. So X what? Or XCl what? Any thoughts?
Would it be 5?
5.
Yeah, just 5. That's right. So it's always, it's always the same because Cl has a -1 charge and so does chlorate. So it still has to match. So to get this working here, whoops, what am I doing? Sorry. No, I'm confusing things here. I'm sorry about that. I'm going to erase all that. Let me erase that. I'll do it again. Sorry about that. I didn't need to put that plus O2 on that side. Do that again. That's what I meant to do. Sorry about that. That's what I meant. Sorry. Okay, so we've got the XCl5 plus the O2. Now, if you count up the oxygens here, we've got 15. So we're doing something similar here to what we did with the hydrocarbon balancing. And I put 15 over 2 over here on the O2. So I have to multiply everything by 2 to balance that out. So if you look at that, you'll see we've got 30 oxygens on the left side. We've got 30 on the right. We've got 2 X's, and 10 CLs and 10 CLs. So everything's balanced there. All right, does anybody have any questions? Okay.
Is this like reverse rust, basically? Reverse oxidation?
Yeah. Yeah, you
Okay.
could look at it that way. You could look at it that way.
Why does the first equation have 15 over 2 in front of the oxygen instead of just 15?
Because that would give 30. If I had 15 in front of the O2, that'd be 30 oxygens. We only have 15 over here. So what I do
okay.
is 15 over 2, which is like 7.5 O2s. So it looks like this.
Okay.
This is O2 here. And I'll show you what 7.5 looks like. That's 7, right? And that's 7.5 O2s. So it's like 7 full O2s and then half of one. If you count them all up, that comes out to 15.
Okay.
Do you see what
That
I'm
makes
saying?
sense. Yeah,
Yeah.
I understand.
Okay. All right. I'm going to show you some other decompositions as well. We've got XCO3, which is going to go to XO plus CO2. So that's a carbonate. And we've got XOH, which also goes to XO plus H2O, and that's called a hydroxide. The last one we've got is this one, which is X dot H2O, which gives X plus H2O. That's called a hydrate. Pretty soon, you'll be doing a lab about that. I think next week, you'll be dealing with some hydrates. And when you heat them up, that's what happens is they have this water associated with them, and then they split apart, and they end up getting the X plus water. All right, does anybody have any questions so far? So
What does the dot in front of X resemble?
It's well, I'll do the hydrate first. Here's an example of a hydrate. CuSO4.5H2O. This is copper sulfate pentahydrate, is what it's called. The dot represents that there's 5 waters of crystallization, which means there's 5 molecules of water surrounding each copper sulfate molecule. This produces that nice blue compound that you've all seen for CuSO4.5H2O. When you heat it, and this is what you'll do in the lab actually, we'll be turning this, this is blue, And this is called the anhydrous salt, which is white. So it starts off as blue, and then once the water disappears, because you've heated it, it turns white, a white solid. And that's just copper sulfate by itself. So the dot there represents how many waters are associated with it. So that one's pretty easy to balance as well. So whenever you see the dot there, you know those are waters of crystallization.
Okay.
Let's look at a hydroxide first. We'll go with XOH4. Now the thing with the oxides is that we know that it's going to be X4 plus because OH is a -1 charge. And that's going to be joining with O2 minus because O takes on a -2 charge because it's in group 6 plus H2O. So when I come up with the formula for the oxide, it's going to be XO2. The reason for that is because I need to have enough of each to balance out the charges. So I need 2 oxygens to balance out that X. And again, don't worry about what the X is. All I'm interested in is what the charge is. And I know what the charge is by the number of hydroxides that are with it in the start of the problem. Now that's not completed yet. To fix this, I need to put a 2 in front of the H2O. Now you can see that I have 4 oxygens and 4 hydrogens on each side, and that would be balanced. Does anybody have any questions about that?
So I'm noticing with the X is I don't know what that, I was looking on the periodic, is that a transition metal?
No, it's nothing. It can be anything.
Oh, so that's a variable, I got you.
I'm trying, well, it could be any element, but I'm saying I always know what the charge is because I know what the hydroxide is. The hydroxide is -1. All I'm interested in is what the charge on X is. X in this case could be tin or lead, for example.
Mm-hmm.
But it doesn't really matter.
Gotcha. Okay, I didn't know which one it was associated with, and I was sort of like trying to figure that out.
Right.
Okay, thank you.
So you'll see problems like this on the test as well. That's why I'm doing it this way. I don't want to do that. Okay. Okay. I'll try something like this. XCO33 gives X something O plus CO2. Now the charge on X here is going to be 6 plus, and the charge on O is going to be 2 minus. Now you might be wondering, well, how do I know the charge of X is 6 plus? Can anybody tell me? How do I know the charge on X is 6 plus?
Because this is in CO up -2.
Yeah, CO3 is -2, and there's 3 of them. So that's a total of -6, which makes the X here. Let's see, CO3, 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 2 minus, 2 minus. And again, you get that off the periodic table. Sorry, the polyatomic iron sheet, polyatomic iron sheet. That means that X is going to be 6 plus. So I'll put this down here a bit. There we go. That's better. So we'll have XCO3 3 gives XO3. Again, it's the number of oxygens needed to balance out that X plus CO2. So I put a 3 in front of the CO2 to balance out the carbons. And if you look at that, you've got 3 times 2 is 6, plus 3 is 9, which balances out the carbonate as well. So that's how you would balance that. All right, does anybody have any questions about those? These are on the test, so that's why I'm doing them. You'll see them on the sample test. I always get questions about them, and people say, oh, what's the X? What's the X? Well, it doesn't matter what the X is. Only matters what the charge is on the X.
So, a quick question. So this is going to be an example of decomposition, right? So you're going to say,
Yes.
so the question is going to be like, if this is decomposing into a
Yeah.
carbonate, then I know that it's going to produce CO2 and whatever. So
That's right.
so always just have CO2, and then it's going to be XO because you have leftovers. Okay.
That's right.
All right.
Now,
So that's. I was just trying to get the format of the question because like I'm not sure like.
well, you'll see when you look at the sample test, okay?
Okay.
But what it asks, there's a couple of questions. There's questions that ask for the formula of the oxide, right, which is the compound with X that has oxygen in it. And then there'll be questions that ask for the sum of coefficients of the balanced reaction.
Okay.
All right, that's what the formatting's like. But anyway, you can look at the sample test. You can see it. They're the last 3 questions, 32 through 34.
Sweet. Thank you.
Okay.
So to find the charge of X, you look at the anion it's connected to, and X is essentially a placeholder element.
Yep.
And then from doing that, you figure out how to balance it. Is that
Yep.
just how you do? Okay.
Just knowing also that the charge on X never changes going from the reactant to the product. The charge on X will always stay the same.
Okay.
I think that's the key there. I know we're doing a lot today, but don't forget, I mean, come on. This isn't the first time you've seen this, right? You've seen this. This is just review, right? It's just review. I'm just going through and reviewing because you've all seen this stuff before. Maybe not the stuff we just did just now, but everything else you've seen. I know. Don't lie to me. Don't tell me you've never seen this before in your life. I won't be impressed if people start telling me that. Dr. Musgrave, I've never seen this before. What are you doing to me? Okay. All right, single displacement reactions. So for this one, you might remember this, and you had this partial activity series. You're not going to need this for the test because the question I'm asking isn't depending on this. It's more depending on these 2 statements here. And that is, if an element is more active than the cation of another element, then the reaction will proceed. So let me do something a little bit more general than that. All right, so you got, let's see, A plus BX gives AX plus B. A is generally solid, BX is aqueous, AX is aqueous, and B is solid. So that's a typical single displacement process. Now, the key information you need is this. If A is more active, you can say active or reactive if you want to, than B. But what we're talking about is a situation. It involves redox reactions and electrode potentials and a lot of other stuff that is sort of beyond the scope here. So I'm just going to say if A is more active than B, this reaction will occur. If B is more active than A, this reaction will not occur. And that's the difference. Now, what is A and B? Now, A is a solid. I call that neutral. Now, B is a cation, and it's going to be aqueous. So that's why we can say A, and I'll say solid, and B, which is the cation, B cation, A solid. And that's how you can tell. So just to give you an example, you won't have this chart, but you won't need it, and I'll tell you why in a second, why you won't need it. But for example, we know that if we were reacting, say, Mg and Al3+, that reaction will occur because Mg is more active than Al according to this activity series. But if I was to take, let's say, Ag plus Mg2+, that will not occur because Mg2+ is not more active than Ag, so that reaction won't occur. So that's what we're doing, is we're looking at the cations and the cations and the solids and where they are in this activity series. Only if the solid is more active than the cation will the reaction occur. So that's the basis of it. So let's look at the kinds of problems. Actually, I'll pull up the test here, and you can see the kind of problem we're dealing with. It's actually not as bad as it seems. On, let's see, what's today? Today is Wednesday, right? Now, remember, there's no school on Monday because it's Labor Day, so there won't be class on Monday. I've got to find the test here. Here we go. And on Wednesday, I'll go over these questions in more detail as they appear here. All right. There we go. So here's what the test question looks like. I'm just trying to shrink this so you can see the whole thing here pretty much. So here is your experiment, and then you get an observation here. The observation is key because the observation tells you whether it reacted or not. If there's no changes, then it means it didn't react. But if it did react, then there'd be something there like bubbling or changing color or solid changes color or liquid changes color, something like that would indicate a reaction occurred. So remember that this business here, if A solid is more active than B cation, this reaction will occur. And if the reaction doesn't occur, it means that the cation is more active than the solid. So that's going to be the premise that we're acting on here. And this observation could be no changes for no reaction or anything else. Anything else will give a reaction here. So what are we saying out of that? So reaction, yes or no? The answer in this case would be no. The neutral element, well, that's going to be the solid. That's going to be the gold. The cation is going to be the tin 4+. Which one's more active? Which one's less active? Well, if there's no reaction, it means the tin would be more active. If the gold was more active, there'd be a reaction. So it means the tin must be more active. So you've got all these answers here, and they're just combinations of everything I just talked about. So in this case, the answer is no. Gold is the cation. Tin 4+ is the cation, and the one that is going to be more active will be the tin. So the answer would be this one here, and that's what you'd put down. Now, had there been some sort of reaction here, then the answer would have been gold, would have been the more active. So that's the difference there. If there's no changes, it means the cation's more active. The element that forms a cation is more active. And then if there is a reaction, then it means that the one that's solid is the more active of the two elements. That's all there is to it. Does anybody have any questions? All right, so what I would want you to do is you should take a look at this yourself and see how you're doing with it. And everything that relates to module 6 here, I think starts at number 24 on the sample test. So you should probably try some of those yourself, see what the formatting's like. I'm going to go through this more on next Wednesday, because I won't see you on Monday. If you have any questions, you can always call me or email me, and I can answer any questions you might have. But you should take a look at the sample test, and we'll go through it more on Wednesday. Does anybody have any questions? Okay, well, we'll leave it there for today then, and I will see you. If you want to hang around and ask me anything, you may. That's fine. So I'll see you all later.
So the test and the homework is due next Friday?
No, the homework, let's have a look at the syllabus here.
Or next Friday, that's what I meant.
Now, let's have a look. I'm just checking. I don't think that's true. All right, per the syllabus, the homework is due 10/6. And
no, that's test 2.
Test 2. Sorry, 9/13. Sorry, 9/13 and 9/14.
Okay. When is the 13th? Let's see.
The 13th is Sunday, right?
Yeah, it is Sunday.
Right. And your test is due that Monday, the 14th.
Okay.
Now, the 7th is a holiday. 9th is the review day that I've set up here, where I'm going to go over the test.
Okay.
All right.
All right. Have a good day.
All right, no worries. Okay, let's see who else is here. Richard, nope, that's just me. Okay.